Welcome to S1 Lesson 9, looking at the binomial and Poisson distributions, in particular the Poisson distribution. So before we start, if you have access to the presentation slides, it'd be good to have a printout so you can make your own notes as we go through the presentation, and you can make a record of your thoughts and feelings and ideas. Definitely make sure that you've got pen, paper and calculator. The idea of a video is to be interactive and give you the opportunity to have a go at some examples during the course of the video and to check your own work. So where are we in the S1 syllabus? We've covered the area of probability. We've looked at discrete random variables. Now we're exploring the binomial and Poisson distributions, in particular today focusing on the Poisson distribution. What is the Poisson distribution? Well, the Poisson distribution is used to calculate the probability of a number of occurrences of a particular event in a measured space. Now this can happen in a number of ways, and so the following examples are good examples of situations we can model using a Poisson distribution. So the number of phone calls in an hour, the number of bacteria per milliliter of water, the number of floors per meter of fabric, the number of insects per meter squared. Notice in each of these examples we are counting something, i.e. phone calls, bacteria, floors or insects, in some sort of measured space. So here we have time, we have volume, we have length, we have area. Now, there are things that link these all together. What's important about the Poisson distribution is that the events occur independently of each other. The events occur singly, so one at a time, and that the events occur at a constant rate. That is, that the average number of occurrences in an interval is proportional to the width of the interval. Put simply, if you get on average to a call centre 30 phone calls an hour, then in 2 hours you'd expect 60 phone calls. In 3 hours you'd expect 90 phone calls. Okay, so how is the Poisson distribution defined? Well, if you have a discrete random variable x that has a Poisson distribution with a mean of lambda, first, whenever we do any questions, we make sure we state this using the following notation. So x is distributed with Poisson, and this is our mean lambda. We can calculate the probability that the discrete random variable x takes a particular value x using this formula. It doesn't look particularly great, but it's not too bad to use, to be fair. So let's have a look straight away at an example. We have a discrete random variable x has a Poisson distribution with mean of 1.3, and we want to find the following probabilities. Probability x equals 0, probability x equals 3, and probability x is greater than 2. So starting off, as I said, state the distribution we're using. So x is distributed with Poisson mean 1.3. We know that probability x is equal to x is given as e to the minus lambda times by lambda to the power of x over x factorial. So if I calculate the probability x is equal to 0, we get e to the minus, well, our lambda value is 1.3, times by lambda, which is 1.3. This x value is 0 over 0 factorial. If we put this into a calculator carefully and work through, should get an answer of 0.2725 to 4 decimal places. And in today's video, I'll be working to 4 decimal places consistently. Next, probability x equals 3. It's done in exactly the same way, e to the minus 1.3 times 1.3, this time to the power of 3 and over 3 factorial. If you put this into a calculator and work through it carefully, again to 4 decimal places, we get 0.0998. Okay, so then probability x less than 2. Greater than 2. Now, this is going to be very similar to what we did in the binomial distribution in the last video. We're going to work this out. Instead of trying to work out all the possible probabilities of how many occurrences can happen, because this could be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, etc., all the way up to infinity, what we need to do is we need to take the total probability, which is 1, and subtract the probability of having less than or equal to 2 events. And today you'll find a lot of the techniques we use are very similar to the binomial distribution. So this will be calculated by doing 1 minus probability x equals 0 minus probability x equals 1 minus probability x equals 2. So writing that out, we already have probability of x equals to 0, 0.2725. So now minus probability x equals 1, so we get e to the minus 1.3 times 1.3 to the power of 1 over 1 factorial. Minus probability x equals 2, so that's e minus 1.3 times 1.3 squared over 2 factorial. So working through this, we get 0.2725 minus 0.33543 minus 0.2303. And again, put this into your calculator carefully and work through it. You should get an answer of 0.1429. The ideas here are exactly the same as the binomial. The only real difference is that we've got a different formula here to use. It's a good idea when you're working through the Poisson distribution, just whenever you get any questions that aren't an exact value as well, just to take the opportunity to practice using that formula. Sometimes in the exam they give you questions where you can't use tables, and sometimes in the exam they also ask you specifically not to use tables. So here's one for you to try out. We have the discrete random variable x that has a Poisson distribution with mean 2.5. Find the following probabilities. So if you pause the video at this point, have a go at the question for yourself, and then resume it once you've had a go at the question, and we'll go through that answer. Okay then, so let's go through this answer. Again, I'll just start by stating the distribution. I will state the formula as well, just so we've got it to reference while we're working through. So it's e to the minus lambda times lambda to the power of x over x factorial. So first, we wanted to do probability x equals 0. So we get e, this time my lambda is 2.5, so to the power of minus 2.5, times by 2.5 to the power of 0 over 0 factorial. Put this into your calculator carefully. You can do it in one go, type it in, and then we should get an answer of 0.821, again to 4 decimal places. Next, probability x was equal to 4. So e to the minus 2.5 times 2.5 to the power of 4. So this is all that's changed is the power of 2.5 and the factorial underneath, that's the power of 4. If you work through that carefully on your calculator, you should come out with an answer of 0.1336 to 4 decimal places. Okay, so finally, we then wanted the probability x was greater than or equal to 2. So very similar to what we did in the previous question, except this time I'm going to include 2 as one of the probabilities. So I want to, again, find the total probability, but subtract all of the outcomes that are not included in this. So that's probability x less than or equal to 1. So we get 1 minus probability x equal to 0 minus probability x equal to 1. So when we work through this, we already have the probability of x equal to 0. It's 0.0821 minus probability x is equal to 1. So we're going to get e to the minus 2.5 times 2.5 to the power of 1 over 1 factorial. And so this will give us 1 minus 0.0821. When you work through carefully on your calculator to calculate this, you should get an answer of 0.2052 to 4 decimal places. And when we work through this whole calculation carefully on your calculator, you should then get an answer of 0.7127. Okay, well I hope that made sense that you're now feeling confident about using the Poisson formula. Just like the binomial, you can see that using the Poisson formula can be a little bit laborious, so we have Poisson tables that will help us. Poisson tables, again like the binomial distribution, will tell us the probability that x will be less than or equal to x. So it uses a cumulative probability function. So it means it accumulates all the probabilities up to this value. So let's have a look at the Poisson tables. Across the top, I know that there's an m there, really that should be a lambda, that's just the Poisson tables I've chosen to use. Across the top, these are our values of lambda, and then down the left hand side and the right hand side, which is quite useful, is the number of occurrences. So probability, let's say x is distributed with a Poisson of mean of 1.6. Probability x is less than or equal to 4. If we have a look, here's my 1.6. I'm just going to highlight it on the left hand side here, simply because it's closer to this right hand side. Less than or equal to 4. So if I just draw a line there, we can see that the answer would be 0.9763. Okay, so let's have a look at an example using the tables. Starting to look at some contextualized problems now. We have an insurance company. It receives on an average of 10 claims per week. We want to find the probability that in 1 week it receives no more than 4 claims, at least 13 claims, and between 8 to 12 claims. So one of the things you'll have to do is interpret questions. We're going to interpret this as inclusive. So it's going to be calls from 8 to 12 inclusive, so including 8 and 12. In an exam, it would more likely be very, very specific about this. Okay. Now, first thing to do is set up our distribution. So we're going to say x is the number of claims, and it's going to be distributed with a Poisson, and it was 10 claims per week. So Poisson with a mean of 10. We're looking to find probability of no more than 4 calls. So that's a probability x is less than or and equal to 4. Now we can go straight into the table and read this off. We're looking for a Poisson mean of 10, so I'm looking at this end column here. What I want to do is just read across, and if I use a highlighter pen just to show you how I've read across. So reading across x less than or equal to 4, reading across here. I'm not going to actually go over the value. You can see we get an answer of 0.0293. So let's just make a note of that. 0.0293. Okay, next was probability x was we had at least 13 claims. So that's probability x is greater than or equal to 13. Now we know that that could go up to an infinite amount of claims. So what we're going to do is we're going to reverse the idea. We're going to take the total probability 1, and we're going to subtract all the events that all the occurrences up to but not including 13. So probability x less than or equal to 12. So we're going to get 1 minus. If we go to our tables, I get a highlighter pen. We want x less than or equal to 12. So coming across very carefully, and then you can see I get the probability of 0.7916. So 1 minus 0.7916. Type this into my calculator and work through it, and we get a probability of 0.2084. Finally, we said we wanted to work out the probability of between 8 to 12 claims inclusive. So probability 8 is less than or equal to x is less than or equal to 12. So the way we approach this is we're going to do the probability, sorry, I missed that out, that's a bit silly. We're going to do the probability of getting up to 12 claims, except I don't want to include the probabilities for the claims from 0 to 7. So I'm then going to subtract probability of x less than or equal to 7. Now I already know the probability of x less than or equal to 12, so that's nice. I can put in 0.284 straight away there, minus, so I just need to now find the probability of x less than or equal to 7. So just highlighting again, coming across from, oops, highlight pen might be better there. coming across from 7 all the way across, just carefully. And remember, use a ruler or a piece of paper for you to do this yourself. You shouldn't really be marking on here. This is just so I can emphasize what I'm doing to yourselves. Okay, so we get an answer of 0.2202. Let's get the right pen going. So minus 0.2202. Now I've got a silly mistake there. This, of course, was the probability of it being greater or equal to 12. Probability of being less than or equal to 12 was this one here, so I've got 0.7916. Okay, so taking the difference there, we get 0.5714. Okay, well, I hope my little error there didn't confuse you. Remember that this here was my probability, x less than or equal to 12. Just made a mistake when reading above here. Other than that, I hope you can understand the tables now, because what I'm going to do is I'm going to give you an example to try it for yourself. So, the average number of floors in 10 meters of chain produced by a machine is 6. Find the probabilities that the number of floors found in 10 meters of chain is less than 3, greater than 6, and between 4 and 10. And again, I'm just going to say here, inclusive. So at this point, I want you to pause the video and then unpause it when you're ready to check your work. Okay, so welcome back. Let's have a look at the answers to this then. So remember, start off, state distribution. We had 6 floors in 10 meters, so the mean is 6, so x is distributed with Poisson mean 6. First of all, we wanted to find probability of x less than 3. So there was less than 3 floors. Remember, we want to do this using weak inequalities, so this is actually probability of x less than or equal to 2. So if we go into the table, we're going to use a highlighter pen again to help us highlight where we are. So here's Poisson mean 6, so I'm just going to do a little column down the right of it. Not particularly straight, but it's just to emphasize which column we are focused on. I want probability of x less than or equal to 2, so we can see we get 0.0620. So 0.0620. Okay, then we wanted to find the probability that there were more than 6 floors. So probability x is greater than 6. This is essentially saying, well, for this, we don't necessarily need to use a weak inequality, but what we want to do is we want to think about, okay, well, I want the probability of 7 and greater. So again, we have to do total probability minus all those events other than 7 and greater. So that's probability minus probability of x less than or equal to 6. Because of course I can go up to 6 and I can include 6 because we want it to be greater than 6. So 1 minus, again, let's go to the tables and get a reading for this. So probability x less than or equal to 6, we can see here is 0.6063. So 1 minus 0.6063. Just type this into our calculator carefully and get ourselves an answer of 0.3937. Finally, wanted to find a probability that there were between 4 to 10 floors. So we said inclusive, so we're going to include x equal to 4. So that's going to be x lies in between 4 and 10. So we have to find out the probability of all the way up to 10 floors. But then since I don't want to include the floors less than 4, we're going to subtract probability x less than or equal to 3. So go into our tables, take a reading using a highlighter pen. So x less than or equal to 10, first of all, is 0.9574. And then probability x is less than or equal to 3 is 0.1512. Okay, so let's then finish off our work. So we get 0.9574 minus 0.1512, and so you should finally get an answer of 0.806. 2. Okay, well, I hope you feel comfortable now using the Poisson tables. We're going to extend this idea just a little bit and use one of the ideas that we discussed earlier. So one of the ideas that was discussed earlier was that Poisson distribution, the events occur at a constant rate. That means that if we had 30 phone calls an hour, we expect 60 in 2 hours, 90 in 3 hours, etc. So we're going to use this idea in example 3. We have a magazine and it has on average 1.5 spelling errors per page. For an article of 6 pages long, find the probability that there are exactly 5 errors, less than 12 errors, and 1 mistake on every page. Okay, so really we're starting off, if we say X is distributed with a Poisson mean of 1.5, so this is 1 page, and then if we say Y is distributed with a Poisson mean, if we're doing 6 pages, the mean will be 6 times as high. So 6 times 1.5 is 9. And I'll just put that in as a little bit of extra work in there for you, just to remind you. Okay. So it's important that we state the original distribution and then a modified distribution for this larger range of days or large measured space. What we're then asked is, in those 6 pages, find the probability that there are exactly 5 errors. So probability Y is equal to 5. Now, I would take this opportunity to practice using the formula. So we get e to the minus lambda, so e to the minus 9, times lambda, which is 9, to the power of our x value, which is 5, over 5 factorial. Work this through on the calculator carefully. You should get an answer of 0.0607 to 4 decimal places. Find the probability next that there are less than 12 errors. So what we're looking at is probability Y is less than 12, or in fact probability Y is less than or equal to 11. So this one's going to require tables to answer the question. We're looking at a Poisson mean of 9, so I'm looking at this column here. So the green line marks all the way up to where I'm going. Again, you don't need to do this on yours, it's just so that I can visualize, make it easier to visualize for you guys. So now I want to do probability of Y less than or equal to 11. So coming across and just reading, what do we get? And we get 0.8030. So 0.8030. Okay, so the third part said, what is the probability that there is a mistake? 1 mistake on every page. Well, probability of there being 1 mistake on every page, so 1 on every page, will be the probability that there is a mistake on 1 page, 1 mistake on 1 page, times the probability of 1 mistake on the next second page, times the probability of 1 mistake on the third page. So since there are 6 pages, it will be the probability of 1 mistake, and let's just add some little notes here. So this is probability P1, probability 1 mistake on single page. And then this 6 is because we're doing probability x equals 1 times probability x equals 1 times dot 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 times probability x equals 1 for 6 pages. Okay, so the way I can work this out then is probability that x equals 1 will be e. Be careful here because we're talking about 1 page, so that's why I've switched to x and I'm not using y. I should have perhaps emphasized that. So p to the power of minus 1.5 times 1.5 to the power of 1 over 1 factorial. all to the power of 6. Now if I put this into my calculator, and I'm just going to break it up into a little bit of steps just so you can check you're doing the right calculations. If I put that into my calculator, I should get 0.3347 to 4 decimal places to the power of 6. And of course, if I use that then exact value, you should then get sort of 0.0014. This might come up on your calculator as 1.4 to 2 decimal places times 10 to the minus 3. Okay, so a little bit of a twist in the question at the end there. So I'm just trying to introduce different things that potentially get asked. Had to be a little bit more aware of what's going on there. This wasn't just a case of finding out the probability of there being 6 errors in 6 pages, because you could have 6 errors on the first page and then none on the rest, etc. This is the probability of finding 1 mistake per page and then multiplying them together because they are independent events for 6 pages. Okay, so let's get you to have a go at one very, very similar. The number of sales per person at a call center can be modeled with a Poisson distribution with a mean of 2 sales per hour. Sales representatives work 4-hour shifts. Find the probability that in one shift a worker has at most 10 sales, at least 5 sales, and 1 sale on every hour of their shift. So pause the video now, have a go at it, and then resume once you are ready to mark your work. Okay, so welcome back. Let's have a look at the answer to this. So again, let's define our distribution here. We started off with x. Let's say this is for 1 hour. So x is going to represent the distribution for 1 hour. It is a Poisson mean of 2 because that was what it was given. So now for 4 hours, let's use y. Y would be distributed 4 times 2. So a Poisson mean of 8. Now first of all, we're asked that in a 4-hour shift, find the probability that they have at most 10 sales. So this is probability that y is less than or equal to 10. Nice straightforward example for us to do. We can just go to the tables and read it from the tables. So let's first of all, we have a Poisson mean of 8. So let's just highlight the column that we're going up to so that it's easier for you to see, understand what I'm doing. We want to find probability x less than or equal to 10. So we should get an answer of 0.8159. 0.8159. Okay, next we're asked to find a probability that there's at least 6 sales. So we're saying y greater than or equal to 6. So we know at this point it's the total probability minus the probability of being less than 6. So x, sorry, not x. Let's make that clear. Y less than or equal to 5. So we're going to go to the tables and take this reading. Y less than or equal to 5 is 0.1912. That was, oh sorry, misread that as 5 sales. So let's just amend that quickly. So apologies. Very quick. So it's just where I misread it from the slide. So that's y less than or equal to 5. So this should be y less than or equal to 4. So if we go back, let's just get rid of that a second. We're going to say, okay, highlight pen, probability of y less than or equal to 4. So it's 0.0996. So that's better. So apologies for a small error there. 0.0996, which gives us a probability of at least 5 sales of 0.9004 to 4 decimal places. Finally, the last part of the question said find the probability of 1 sale per hour of shift. So probability 1 sale per hour for 4 hours. So this is going to be the probability. Again, we're going back to x here now because we want to find probability of the number of sales in an hour. So this is a probability of 1 sale in 1 hour, so it's probability of x equal to 1. We're then going to multiply that by probability of x equal to 1 for each of those hours, so it's going to be to the power of 4. So again, personally, I would use the formula in order to work this out. So I've got e to the power of minus 2, because that's the mean, times 2 to the power of 1 over 1 factorial to the power of 4. I'll break it down just so you can check the different parts of your question. So this should give you 0.2707 to the power of 4. Remember, use the exact figure on your calculator. When you work this through, you should get an answer of 0.0054 to 4 decimal places. And again, you might find this comes up in your calculator as 5.4 something times 10 to the minus 3. Okay, I hope that all made sense and that you're starting to feel confident working with the Poisson distribution. I'm actually going to try an exam question now. Okay, so exam question. It'd be a good idea for you to try it out. So have a go at it, see how far you can get through it, and then we will go through it in a moment. So we have David. David is a fisherman. The number of fish he catches in T hours has a Poisson distribution with mean 0.6 T. He fishes for 5 hours. Find the probability that he catches exactly 3 fish, at least 3 fish, and in part B, it says one day the probability of catching fish was no fish was 0.5. For how long did he fish? So just a little helping hand here, 0.6 T means the mean will be 0.6 times however long you are fishing for. So have a go at that question, just see how much you can get done for yourself. And then once you're done, we'll go through it. Okay, so let's have a look at the answer to this. We were told x is a distribution, Poisson mean 0.6 T, and we're told that the T time is 5 hours. So this leads to x being distributed with a Poisson mean 0.6 times 5, Poisson mean of 3. So a couple of marks for that first part, and it's important, as with the binomial, that we always state the distribution. It wasn't too tricky in the end, I don't think. Once you've done that, though, the rest of the question is quite straightforward. First of all, we want to find the probability that he catches exactly 3 fish. So I would again use the formula for this. So e to the minus 3, because that's the mean, times by 3, because that's the mean, to the power of x, which happens to be 3 as well, over 3 factorial. If you carefully work this in your calculator, you should get an answer of 0.02240 to 4 decimal places. Part 2 wants the probability that he catches at least 3 fish. So probability x is greater than or equal to 3. Well, as we've seen a few times today, if it's greater than, we want to take the total probability and subtract the probability of getting less than that amount. So saying x less than or equal to 2. So this will be 1 minus, and let's have a look at the tables to get this reading. So the column we're interested in is Poisson mean of 3. So just highlight where I'm actually reading across to. We want the probability of x less than or equal to 2. So just reading across at 2, and we get 0.4232. So just finishing off 0.4232. Put this into our calculator, and we should find probability of catching at least 3 fish is 0.5768. Now, the last part of the question, let's just go back and recap that. One day, the probability of catching no fish was 0.5. So for how long did he fish? Okay, so we're told probability x equals 0 equals 0.5. This is a question where you're going to have to use the formula to find this. If I was to calculate the probability of x equals 0, at the moment all I know is that x is distributed with a Poisson mean of 0.6t. And we're going to have to work with this 0.6t because I'm trying to find 0.6t. So what we get is e to the power of minus 0.6t is equal to, sorry, a little bit skip ahead there, times by the minus, the 0.6t to the power of x, which is 0, over 0 factorial, and this is equal to 0.5. Now, t to the power of 0 is 1, 0 factorial is 1, so what we get left with is actually 0.6e to the minus 0.6t t equals 0.5. And now I have an equation in E to solve. So let's divide by 0.6. If we divide by 0.6, we get e to minus 0.6t equals 5 over 6. If I take natural logs of both sides, then I get, on the left-hand side, I get left with minus 0.6t, and on the right-hand side, we get natural log of 5 over 6. If I now divide by minus 0.6, we get that t is equal to, and so I just want to do log of 5/6 divided by minus 0.6, and if you work through that, you should get an answer of 0.30 hours to 2 decimal places. Okay, well, that was a bit of an extension question there. It just leaves us one thing to look at with the binomial for the Poisson, and this doesn't get explored too much because of the simplicity of it, and you'll see why now. Last thing to remember is that we've been working all the way through. We know that the Poisson distribution is defined by its mean, but also the variance of the Poisson distribution is the mean. In S1, there's no need to go into any further detail than actually knowing these facts. It's very rare that problems are based around the variance of a Poisson distribution because of the simplicity of it. You may be asked potentially to find the standard deviation just so we can acknowledge that the variance is the same as the mean, but nothing much gets done with it. Okay, so that's it. That's the Poisson distribution. At this point, have a go at the Poisson distribution exercise, and then once you feel confident, attempt assessment 9, which is the Poisson distribution. Okay, well, I hope everything made sense in the video. I hope you feel confident enough now to attempt and independently study the rest of the Poisson distribution. Make you prepared for the next video. Thanks.